All right, so I want to work out one problem with osmotic pressure. In this problem, we're going to actually try to find no, we're not. We're gonna find the osmotic pressure at 25 degrees Celsius in a solution that contains starch and water. And we're given the molecular weight of starch. It's quite large, 32,400 grams per mole. That's not a typo. Starch is a really huge thing. Okay, so I've done a couple of things here for you. We need to find the molarity of starch in order to find the osmotic pressure. So in the first line here, I've taken the mass of starch, used the molecular weight, and found the moles of starch. And then in the second line, we calculated the molarity using the volume of solution, 100 milliliters or 0.1 liters. And so we end up with 2.46 times 10 to the minus 4 for our molarity. So hopefully that's a couple easy calculations for you. And then to find the osmotic pressure, we simply plug into our equation. And it's important to note that, well, first of all, starch is a non-electrolyte, so I is going to be equal to 1. I'll plug in our molarity, 2.46 times 10 to the minus 4. And you need to make sure that you're using the right gas constant. And this one is 0.0821 liters times atmospheres over moles times Kelvin. And since we have Kelvin in our gas constant, we need to use Kelvin for our temperature. So 25 degrees Celsius is 298 Kelvin. Kelvin cancels. And this is moles per liter. So moles per liter is going to cancel with liters per mole. Kelvin cancels, so we're going to be left with atmospheres, which is a perfectly fine unit for a pressure. And we end up with 6.02 times 10 to the minus 3 atmospheres. Okay. Questions on that? Pretty straightforward. Some more interesting calculations come in when we use colligative properties to determine the molar mass of various solutes. And so here we have a solution of organic compound. I'm using this term, I picked this out on purpose. There's a problem in your book that uses organic compound, and I want you to know that that essentially means non-electrolyte. And so I equals 1. So a solution of an organic compound was prepared by dissolving 0.461 grams of solute in 100 grams of carbon tetrachloride, CCl4. The freezing point of the resulting solution was lowered by 0.274 degrees Celsius. And we want to find the molar mass of the solute. So we want to find grams per mole. Okay. We're going to use our freezing point depression equation. We're talking about lowering the freezing point. And so that's given here, delta TF equals minus I times K sub F times the molality. And I also did give you the K sub F here in the problem. If we rearrange this equation, we'll end up with the second one there, where we're solving for the molality. And from there, we can plug in what we know. So we'll say that molality is going to be equal to the change in the freezing temperature, which we said was 274 degrees Celsius. There's a minus sign here. Okay, so we're doing freezing point depression, so the temperature goes down. We have to recognize that that is a negative. All right. I is 1 in our denominator, and then K sub F for carbon tetrachloride is 29.8 degrees Celsius per molal. When we work through our units, we're going to end up with 1 over molality, which is molality, which is good. And we should get 9.19 times 10 to the minus 3 moles of the compound per kilogram of solvent. Okay, that's just restating the units on molality. And I'm doing that because that's not what we're looking for in the long run. What we really want is grams per mole of the solute. So we know that in this solution there we used 100 grams of carbon tetrachloride. So we know the mass of our solvent. So let's just rewrite our answer here. 9.19 times 10 to the minus 3 moles per kilogram of solvent. And 100 grams of carbon tet is 0.1 kilograms. Which means we have 9.19 times 10 to the minus 4 moles of solute in that solution. Still not what we want. We want grams per mole. Okay? The other thing we're told in the problem is that we started with 0.461 grams of solute. Okay, we put that in the solution. And from all of our calculations we've done, we know how many moles that is. So now we can simply take the grams that was given in the problem, 0.461 grams of solute, and divide by the moles that we just calculated. Oops. Is that right? Yeah, that's right. And we'll end up with 501.6 or 502 grams per mole. Okay. Questions on that? Okay. Cool. This figure is just from your textbook. I want to cover this just very briefly because this is an application of osmotic pressure in real life. So this figure is supposed to be showing you some red blood cells. And the important thing here to look at are these terms: isotonic, hypertonic, and hypotonic, and what's going to happen to the cells in those different solutions. So in an isotonic solution, the concentration of ions in the medium outside of the cell and that inside of the cell are equal. And so you have equal transport of water in and out. That's what these equal arrows are trying to show you here. So there's equal transport inside and outside of the cell. And so the cell does not change shape. In a hypertonic solution, there's a high concentration of solute outside of the cell and a low concentration inside of the cell. Okay. So low solute. And so this is just like our picture for the osmotic pressure, whether the water, the solvent, is going to move from low concentration to high concentration. So we see a net movement of water from the cell to the medium. And we see a shrinking of the cell. In a hypotonic situation, the solute concentration outside of the cell is low, high concentration in the cell. And so to equalize that pressure, water moves into the cell. And so, yeah, so that's hypotonic versus hypertonic versus isotonic. Okay. This is in the book. Feel free to take a look at that, read through it. Yeah. Cool. Questions on that? Okay.